Good morning. So today I'm going to be presenting on the effect of AC polarity balance on submerged arc welding of chromium carbide overlays. A little bit of background. Chromium carbide overlays are commonly used. We had an industrial partner. They were looking at chrome carbides and especially interested in optimizing their process for thinner submerged arc weld overlays. And so that's why they ended up coming to us, and then we worked on ways of improving their overlays. So a little bit of background now and the purpose of my research. Really, we wanted to examine the effect that the balance of AC welding had on the microstructure and some of the other properties such as the dilution and the heat input and the carbide size. The main goal really was to minimize the amount of dilution that we're seeing in the overlays in order to produce better quality welds. Now, a little bit of background, especially in Alberta, the cost of wear is huge and it's a big problem. Wear parts can lead to downtime and to failure. This can be a big deal, especially in oil sand operators. It can be a couple $1 million a day when they're sitting idle because of a failure in one of the production lines. So one example, not including the cost that a failures would cost, is just the amount of wear parts that a single oil sand producer goes through, and the labor involved in reinstalling parts is upwards of $40 million a year with just a single operator. And we have quite a few different companies up there exploiting the oil sands, so that adds up quite quickly. A little bit of background also on just overlays in general. If you're not familiar, we're really just adding a hard wear-resistant material to a cheaper, tougher base material. Chrome carbide overlays in particular are used in a huge variety of different industries. This includes agriculture, mining, and oil and gas. Specific examples of their use are truck bed liners, and I'm not talking about pickup trucks here. I'm talking about those pictures where you see someone standing next to a tire and the tire's bigger. They line those dump trucks with chrome carbide overlays to protect them from wear. Also, throughout the processing of the oil sands, in chute liners, sizing screens, they also use chrome carbide overlays. Things that we see regularly in Canada, at least, snowplow shoes, those are also lined with chrome carbide. Some of the other liquid handling in pipelines and such, they'll also line huge lengths with chrome carbide overlays at different steps of the processing. So my project in particular, we're looking at at submerged arc welding. And the reason for this is it's the highest deposition rate that you can really get with doing chrome carbide overlays. It's one of the most commonly used in industry right now. So with the process of how we actually applied it though, is we took alloying powder and laid it down in front of the welding torch and then welded over it with the flux and just a plain carbon steel wire. And it oscillates back and forth just to increase the width to 1.5 inches. So now getting into some of the microstructure of chrome carbide overlays, I'm just going to give a quick review so you can have a better understanding of what we're looking for. And to start with, chrome carbide overlays, they often have a primary phase. This is an example where the primary phase is M7C3 carbide and a eutectic. The eutectic in this case is M7C3 and austenite. And what you find is we use it as a wear-resistant material because the hardness of the carbide is much higher than that of, say, quartz or silica, which is 900 to 1200 Vickers hardness. So looking at the actual microstructure, there's something that we have to understand is the actual phase diagram. So this is a ternary phase diagram of chrome, carbon, and iron. So what we find is there's quite a few different areas of this. You can get austenite, ferrite, different carbide types, where the M can stand for chrome or iron. Or in the case of actual production, you have many other alloying elements that can also step into that M position. Now, the most important is probably this M7C3. Now, luckily for us, we don't have to worry about the whole of the actual phase diagram. We can sort of take it down and actually look at just this area, which is the actual only area of interest for us. So with the commercially produced chrome carbide overlays, you find that they can fall anywhere in this sort of range of carbon and chromium amounts. And what this means is that you can have really only three different solidification paths that are possible. Now, that means it can either be hypoeutectic, eutectic, or hypereutectic. So the first one is if it's hypoeutectic. In this case, you have a composition that is that's lower in carbon, and so it's somewhere on this side of the eutectic line. And in this case, the first phase that you have to come out to solidify is austenite. So as the austenite is coming out of liquid solution, or is solidifying, the composition is actually changing towards this line because chrome and carbon is being depleted. Now when it reaches this line, you then end up getting a eutectic structure come out of austenite and M7C3. And this solidification continues until the liquid is exhausted. There's always a chance of getting a pereutectic down at this corner, but for commercial alloys, this doesn't occur because you have enough alloying elements that depress this reaction from occurring. So this is an example of what that microstructure looks like. You get these large primary austenite dendrites filled in between with the eutectic austenite and the eutectic M7C3s. This brings me to the second microstructure that we can get, and that's just a plain eutectic microstructure. And you get this when you're right on the eutectic line or a little bit to either side. And in this case, the solidification path is just like the second half of that hypo. And that's, you have liquid going to austenite and M7C3. And this is one example of the type of microstructure that you can get for that. And you can see the fine austenite and the eutectic M7C3. You can tell it has a slightly different shape to the carbides compared to the primary ones, and much finer than the primary carbides. This brings me to the last sort of solidification path that I'm going to go over for chrome carbide overlays, and this is hypereutectic. Now in this case, you have a composition that's going to be somewhere on the right side of the eutectic line, high in carbon and high in chromium. So in this case, you have your liquid, M7C3 coming out of the liquid as the primary phase, and then once again the composition is traveling towards the eutectic line. It reaches the eutectic line, then you're getting the eutectic reaction, or the eutectic solidification. Now this is the example of the hypereutectic microstructure, and now you can see the primary carbides, very different morphology. They tend to have these cores on the inside, and then once again surrounded by the eutectic. So why did I show you those different microstructures? Because there's a big difference between them. The hypereutectic has a much better wear resistance than the hypoeutectic, but there is applications where you prefer the hypoeutectic. And that's where you want higher corrosion resistance and better toughness of your welds. The hypereutectic has a lot of cracking in it. In fact, our industry partner, there was a time where if they didn't have a certain amount of cracking within a distance, they considered that a bad weld. It must not be hard enough. So now, for us, why would we not just do an entirely hyper-eutectic? We're just concerned with wear mostly. We're not too concerned with corrosion resistance or the toughness because it's being applied to the tougher base material. Now, what we actually found with the submerged arc welds is that the ones that were being produced, they had this layering effect. And we were actually getting all three of the different microstructures throughout the width. We're getting hyper-eutectic at the top, eutectic, and then hypo. And you can see the primary austenite in the bottom one and the large primary M7C3s in the top. So the reason that we're getting this is because there is such a large amount of dilution in submerged arc welding compared to some others. And this leads to this inhomogeneous structure. It's a little early for big words. But anyways, so we decided that one way to solve that is to look at AC welding. So what I did is I used constant voltage AC welding, and because I used constant voltage, the wire feed speed and the voltage were set and held constant through all the samples. Now, because those variables are being held constant, it's actually the current that is being varied by the machine. So the important thing with why we chose to use constant voltage was this kept the deposition rate the same. So we were adding the same amount of wire and powder to each weld. So with this, since we were changing the current, we knew that we'd be changing the heat input and the dilution. And this is just a little schematic showing what happens as you increase or as you change the balance. Balance is given in the amount of time that it's spent in positive polarity. So with a 25% balance, 25% of the time you have a positive polarity, and 75% you have a negative polarity. So, and from lots of previous work, we knew that we would be getting more penetration as we actually increase the balance. So what we did is we looked at 6 different samples. We looked from 50% to 75%. If you go any lower than 50%, you start to have problems with arc stability, that sort of thing. And we wanted to look at the lower end because we thought we would get better results than looking from 100 down to 75. So we also looked at the heat input, and the interesting thing to note is that the heat input did increase as we expected as the balance increased. We also wanted to look at the volume fraction of the primary carbides, the dilution, and the carbide size. This is the actual results of the dilution, and you can see very apparently the difference between the 50% and the 75%, especially at the center of the welds. You have a very drastic change. We're going from low 3-4% dilution at the 50% at the center line to 25 with 75% balance. So it made a huge difference. Now, the next step was to actually look at the microstructure and see how this changed the microstructure, because that's how we get an indication of whether or not we have made better overlays by seeing what the microstructure has come out as. So there are a number of important factors that play a role in the actual wear of these overlays. But the 2 main important ones that we wanted to look at for this research is the volume fraction, which is probably the #1 indicator of how well the wear resistance is going to be, and carbide size. And just an example, what we know from experience is that if you have tons of primary carbides, like the picture down here, you're going to get good wear resistance. If you only have a few, you're not going to get as good wear resistance. So what I did was I took hundreds of photos and then stitched them together and got pictures like this. And now, once again, you can see this big change in the microstructure going from 50% to 75%. You can see primary carbides from the top to the bottom in the first couple of micrographs, and then at the end we get back to what we were used to seeing, which was hypereutectic at the top and then hypoeutectic at the bottom. It's a little hard to see in there, but this is just, here's some of the microstructure zoomed in a little bit so you can get a better idea. And you can just see how apparent the difference is in the actual microstructure between the different samples. So when we plot that all out and get the actual size of the different the size of the carbides and the volume fraction, we can see just how much it actually changes. And it's going from, we're going from 3% volume fraction of the primary carbides to all the way to 21%. Now, the average diameter we also found with the lower balance increased in size, and with the higher balance decreased in size. The one important thing to note too is the fact that we are now getting hypereutectic throughout the entire microstructure. This means good wear resistance throughout the height. You're not going to have good wear resistance at the beginning, then going to worse wear resistance throughout. So that way you can accurately establish how long your wear plates are going to last. Which really just brings me to the summary that we were able to decrease the balance, by decreasing the balance in AC welding, we decreased the dilution significantly. This decrease in dilution led to a microstructure that had larger carbides, and as I already noted, the more important thing is this led to more primary carbides and more uniform throughout the height, which should give much better wear resistance. That brings me to the end. I just want to say special thanks to Lincoln Electric for their power source, which we used for all this testing, and Wilkinson Steel and Metal, who worked with us on this project as well. Thank you very much.